for 1/6. So the process for solving equations using logarithms, the first thing you have to do is you have to isolate the exponential term. So you want to end up with something like some a to the x equals p. After that, you're going to take the natural log of both sides. So we'd have something like ln of a to the x equals ln of p. Once again, I think I said this before, if you know how to work with other log bases and you want to use other log bases, go right ahead. You're going to bring the power down. I'm going to say exponent, actually, because sometimes it's more than just a number power, and you usually want to take the whole entire frickin' thing out. So bring the exponent down using log properties. So then you'd look like something like x ln of a equals ln of p. And then finish solving for x using algebra. So in this little simple case that I have going on here, we'd have to divide both sides by the natural log of a. So those are kind of the steps that you're going to follow to be able to solve these equations when we want to solve for the thing that's in the exponent. So let's look at a couple of these. So I want to solve for t when I have 3 to the t equals 10. First step, isolate the exponential. Already done. I don't have anything attached to this 3 to the t. It's already isolated. Step 1, done. Step 2, take the natural log of both sides. Whoa. Step 3, bring the power out. Step 4, finish solving for, well, in this case, t, whatever variable you're looking for. So I need to get that natural log of 3 away from the t value, so I have to divide both sides by the natural log of t. Sorry, natural log of 3. Punch that sucker into a calculator. You're going to get 2.096. In terms of Wiley, I think they'll usually want the decimal. For me, if you leave it like this, the natural log of 10 divided by the natural log of 3, I will count that as correct. That is technically a correct way to say that. If you want to switch it over to the decimal, that's right too. I'm saying I'll accept either. But with Wiley, I'm pretty sure they always want you to actually write the decimal. Questions, concerns? Yeah, I'll give it a couple more seconds because people are scribbling, although maybe they're getting ahead of me, which is fine. Feel free to work ahead of me if you want. I'm going to go to the right, so I'm going to go to problem 3 next. So now I got to isolate the exponential term. Well, the exponential term is this 6 to the t, so I have to get that 5 away. So to essentially get this 5 over to the other side, since they're being multiplied, I have to divide both sides by 5. (25 divided by 5 is 5. Once I've isolated, Take the natural log of both sides. Bring the exponent out. I would suggest taking the entire 6t. If you know what you're doing, you could just take out the t, but I just suggest always taking the whole thing. And then we've got to solve for t, so we have to get t by itself. So I have to move this 6 and this natural log of 8. I often find that some people like to do it in 2 steps, but you can do it all at once. You can just divide the entire thing by the 6 and the natural log of 8 at the same time. Once it catches up to me. There we go. If you want to do the natural log of 5 divided by 6 and then divide that answer by the natural log of 8, or vice versa, natural log of 5 divided by the natural log of 8, take that result divided by 6, go right ahead, whatever floats your boat. Gonna get the same answer. No, let me keep that up. Questions, concerns on that one? Okay. Yep.
So if we keep it like there now, where it's like the natural log of 5 divided by 6, the natural log of 8, that would kind of cut it, correct?
For me, yes. Okay. For Wiley, I think it wants, and I just wrote the decimal that you'll see in 5 years from now. There it is. Because I forgot to finish it out to a decimal. But yeah, if you leave it as this formal thing, I should be clear. Triple check my instructions. I always, if I want you to simplify, it will say it in the instructions. But usually I more care about the process and less about how you write the answer. What up, Jackson?
So we have the 6ln on the bottom. Are you when you're plugging into your calculator, would you plug in ln 5 and then 6 next to the ln 8 after you put the division sign? Or how would you put that in?
You'd want to make sure the 6 and the natural log of 8 are encompassed in parentheses, or else it's going to tell you a different answer than you want it to be.
Okay. All right, thank you.
Yep, so if you ever have more than one thing in a denominator and you're trying to punch it into your calculator, that denominator should go in parentheses.
Okay, that makes more sense.
Alrighty. Next two. We're not doing good on time, but it's all right. So 12, 5, e to the 3t. I need to get this e to the 3t by itself. So I've got to get that 5 over to the other side. You catch up to me, please. Thank you. All I wanted was a little box. Divide both sides by 5. 12 divided by 5 is going to give you 2.4. And then you'll have e to the 3t. Take the natural log of both sides. Why is it so nice sometimes and so absolutely horrid other times? Bring the power out. So bring the 3t out. Whoops. Now we have a little bit of a choice here. The natural log of e is 1. So if you just want to reduce that to 1 and then just divide by the 3, that would be correct. So technically, if I were doing this, I would just say natural log of 2.4 divided by 3 because of the fact that the natural log of e is equal to 1. But if you had the natural log of e down here, you would be completely correct as well. So whatever floats your boat. But the natural log of e is 1, so we can just do natural log of 2.4 divided by 3 to give us 0.292. Yeah.
You have to state that you know it's just 1.
No, you can just reduce it. You don't have to say, I'm reducing this because I know it's 1. And so for this last one, it's slightly different because we want to isolate the e to the t minus 1, but now we have subtraction instead of multiplication, so we're going to have to add 5 to both sides first to isolate that exponential term. Take the natural log of both sides. Bring the entire power out. Now, since that has subtraction in it, put it in parentheses. In this case, it doesn't quite matter because the natural log of e is 1, so that kind of goes away. But if that was a natural log of anything else, you'd have to distribute it first. Well, actually, you could just divide both sides by it. Any algebraic way you could deal with that, you could. But you might not deal with it correctly if you don't have the parentheses around the t minus 1. But natural log of e is 1, so I'm just going to kind of drop it. So we essentially have t minus 1 equals the natural log of 10. So t equals the natural log of 10 plus 1, which is 3.3. Questions, concerns? All right, the last idea in 1.6. I'll leave this up for another couple seconds. Well, actually, I can scroll down a little bit. There we go. The last idea in this section is, so what we presented at first, so this is kind of getting a little scrunched by the things we just did. We were writing things as p naught a to the t. Well, there's another way we could write exponential functions. And there's a completely other form that looks like p naught e to the kt. Now, in these cases, we have these relationships between essentially the thing with the k value and the thing with the a value. And I'll talk about that a bit more in a second. But this k value is going to be called the continuous growth or decay rate. So at this point, moving forward, we might see one example in 1.7, if I can scrap it in there real quick. If you see the word continuous, it will be the e to the kt form. If you do not see the word continuous, it's the a to the t form. So the word continuous is really going to, be our real big tip off of which form we're now going to have to use. Now remember way back when we were starting to talk about exponential functions, we kind of had two options, growth or decay, and it depended on what your a value was. So if your a value is greater than 1, we had exponential growth. And then if a is between 0 and 1, it was exponential decay. We're going to have similar relationships for the k value. So if a is greater than 1, then its associated k value, because we can always find essentially the equivalent form. So even if you're given 1, you can always jump over to the other, which is what we'll see in a hot second. So if a is greater than 1, then the k value would turn out to be positive. So if k is positive, we have growth. I'm going to stop writing the word exponential because I'm being lazy, but it's technically exponential growth. And if a is between 0 and 1, k will end up being negative. So if you're ever given a k value that's negative, you know it's decay. Or if you see continuous decay, that's weird phrasing, but decaying at a continuous rate of, you would know that that would tell you continuous tells you the k value, decay tells you it's negative. Now, again, we can always kind of jump between the two forms. If we have one of them, we can find its equivalent other form. How the heck are we going to do that? Well, I'm going to scroll down really quick, but then I'm also going to go back to this idea right here. Look at those two forms. What is the only thing that's different between those two forms? the a and the e to the k. Everything else is the same. They have a t in the exponent, the p naughts don't change, and the other p doesn't change. So the only thing that's different between the two forms is the a and the e to the k. So to jump between the two forms, use this. Because if they have to be equivalent forms, those two things must be equal to each other. Because everything else is the same. Those are the only two things that could differ. So if we set them equal to each other, they must be the same equation. Or demonstrating the same equation. So say I want to convert to the other exponential form for these ones here. So as I just said, the p naught doesn't change, right? The p naught, it doesn't matter which equation I'm looking at, the p naught's still p naught. So for our new equation, the p naught's still going to be 1000. So we essentially have an e to the kt, and we want an a to the t. Well, p naught is just p naught, and then I'm going to use this relationship that I just told us to use. So I'm going to have a, don't know what that is equal to e to the k, which in this case is 0.05. Remember, e is a number, so you just punch that sucker into your calculator. E to the 0.05. E to the 0.05 is approximately equal to 1.051. You've got all you need. You can write the equation now. It's that simple, and hopefully it seems simple. I should avoid the word simple. So our equation in the other form would be 1000, and that looks like a 6. 1000, 1.051 to the t. Done.